We just learned that derivative of sine inverse of x, for example. Let's just do those one at a time. We just learned that derivative of sine inverse of x was 1 over the square root of 1 minus x squared. So what do you think it is? The integral of 1 over the square root of 1 minus x squared. Give me a function whose derivative is this? Sine inverse of x, right? So the answer to this one would be sine inverse of x. You know, who would have thought such a thing? Because think about it. If you wanted to integrate this quantity with u substitution, let u be 1 minus x squared, you would need to have an x dx on the top, right? And there is no x dx. So this is one of those integrals that u substitution does not work. And somehow a very complicated function comes out as an answer, sine inverse of x. Again, who would have thought? But it works. And what about this one? The integral of dx over 1 plus x squared. Once again, can you do this one with u substitution? Like let u be 1 plus x squared? No, because there is no x dx on the top, right? U substitution doesn't work there. But we just learned a function whose derivative is 1 over 1 plus x squared. So which function is that? Inverse tangent. So the antiderivative of this quantity is tangent inverse of x. And again, this last one you do not have to memorize, but that one turns out to be secant inverse of, I believe, absolute value of x plus c. Again, the first two, I would ask you to memorize, but if you've already memorized the derivatives, the integrals are really a natural conclusion of those. So you really just know one or the other. It's just the other one is automatically comes from the other. Okay, now, finally, I'm going to give you one last set of formulas, and I promise there are no other formulas today because I know we did a lot of formulas. But these are going to be more general. When I say more general, instead of having a 1, you could have any number here, not just a 1, okay? So if you have any number, such as a, the number a, this is what the answer turns out to be. So if you have the integral of 1 over a squared minus x squared under a radical. Again, how does this differ from the previous? We had 1 minus x squared there, right? So there a was 1. But it doesn't have to be. It can be any number. Then the answer changes slightly. Then it becomes sine inverse of x over a. And if you are so inclined, you can differentiate the right-hand side, and you'll be able to show that that will give you the left-hand side. Okay, and finally, the antiderivative of a squared plus x squared in the denominator equals, the moment you see the sum of two squares on the bottom, think about the tangent inverse function. And the rule says if you have a instead of having a 1, if you have the number a, then it's going to be 1 over a times tangent inverse of x over a. I want you to notice a difference here. In tangent inverse, there's an extra coefficient, 1 over a up front. In sine inverse, you do not have that coefficient. Okay, this is not a typo. That's the way it works out. And again, if you are curious, why are these formulas so different? I would encourage you then to differentiate this right-hand side and show that you're going to get the left-hand side. And with what we've learned today, you should be able to do that exercise as an exercise. So from now on, I would say, you know, there's one more formula for secant inverse, but I'm not even going to give that to you. I don't ask you to memorize it. If you were just to memorize these two, I think that covers everything we've learned today. Because this, from here, you can say, okay, if a is 1, what is going to happen? If a is 1, you have integral of 1 minus x squared on the bottom, right? And on the right-hand side, you would have x over 1, which is sine inverse of x. So this is more general. If you know this one, of course, you know the answer when a is equal to 1, right? And also, if you know this one, if I say, what is the derivative of sine inverse? Well, it will be like 1 over the square root of 1 minus x squared. That pattern is also included in this formula. So these two are the most general ones. And if you can remember these, you'll know all the other ones. Okay, now we're going to do some examples with them. Starting with the integral from 0 to 1 of dx over 1 plus x squared. I believe this was pretty much the example I promised you would get to by the end of the class today, or sometime during the class today. Because this we could not do with our knowledge prior to today's lesson. We cannot do this with U substitution, right? It's this one is from 0 to 1 for the first question. Yeah, the first example is from 0 to 1. The integral of dx over quantity 1 plus x squared. So the moment you look at something, the first thought should be, can I use U substitution? And can we? The answer is no. There is no x on the top. Okay. So then we have to say, okay, is there something else I can use? Oh, wasn't there one of those inverse trig functions? Which one? Inverse sine or inverse tangent? Which one do you think works here? The inverse tangent. Anytime you see sum of two squares on the bottom, think about inverse tangent. In this case, your a is 1. So this is going to be inverse tangent of x over 1. It's a simple inverse tangent of x, in other words, right? Because normal is like 1 over the a, but a is 1. It doesn't show up itself. Okay, then plug in the constants, 0 to 1. So we need to find out what is tangent inverse of 1 minus tangent inverse of 0. At which angle is the tangent function equal to 1? Luckily, we've already reviewed this one earlier, right? What angle was that? If you look at your notes on the first page of today's lesson, that's when sine and cosine are equal. Their ratio is 1, right? That happens at 45 degrees. In other words, at which radian measure? Pi over 4. So tangent inverse of 1 is pi over 4. This comes up a lot. It's good to remember this one. Minus, what about tangent inverse of 0? Well, you may remember the tangent function looks something like this. At 0, tangent inverse of 0 is 0, basically. So the final answer will be pi over 4. What about the next one? First question, what should be the antiderivative of 1 over the square root of 1 minus x squared? What is the antiderivative? Sine inverse of x over 1. In this case, it's just going to be x. Now, how did I know this was going to be sine inverse? First of all, I might first be inclined to use U substitution, but there is no x on the top, right? Anytime you have a square root on the bottom, difference of two squares, one has to be a number and one has to be a variable. And further, the first one should be a number. Like if you had x squared minus 1, you could not use this rule. Then you need something you're going to learn in Calc 2. It has to be exactly in this format, a number squared minus a variable squared. That's when you can use sine inverse, okay? And in this case, a is 1, so it's as if you're dividing by 1. Limits are from -1 to 1. So first I need to know what is sine inverse of 1, and then I'm going to need to know what is sine inverse of -1. So you can think of the unit circle, or you can think of the graph of the sine function. We've already done the first one. When is the sine function equal to 1? At which angle is the sine equal to 1? Basically over here, right? What angle is that? In radians, pi over 2. Okay, now at which angle is the sine function equal to -1? Now some of you might say it might be 3 pi over 2, right? Because over here, sine will be -1. But can I accept 3 pi over 2 as an answer? No, it has to be in between negative pi over 2 to pi over 2 range. So go this way then. Negative pi over 2. And the answer is pi over 2 plus pi over 2, or 2 pi over 2, or simply pi. Could we check our answer to this one on the calculator? Certainly. One thing is like you could just say sine inverse of 1 on the calculator. It gives you a decimal answer. Now sometimes I say give me an exact result because I want you to know this. But yet you can check your answer to sine inverse of 1. Do it on the calculator. What are you getting as a decimal there? Could you do that, please? What is sine inverse of 1? And hopefully you're in radian mode. 1.57. And what is pi over 2? Like 3.14 over 2. It's going to be the same thing. Okay, so it's giving it the answer in decimal. Okay. Also, you could do function integration. You can check the whole question from the beginning to the end. Enter the function 1 over 1 radical 1 minus x squared, comma x, comma the limits, and also then you can check the final answer to see if that came out to be correctly. Okay, a couple more examples, a few more. But these are pretty quick if you know your formulas. At a glance, let me just show you one at a time here. So let's just go one at a time. At a glance, do you think this can be done with U substitution? No. Do you think you're going to need tangent inverse or sine inverse? Sine inverse. What is our a here? 16 is a squared. So what is a itself? A is 4. A is the square root of 16. The formula says you need sine inverse of x over a. And what is a? 4. So the answer is sine inverse of x over 4 plus c. Any questions on that one? There was no 1/3 or 1/4 in the sine inverse formula. Only the tangent inverse has that extra coefficient. Okay, for this one, can you do it with u sub? No. What is a here? 3. Which function are we going to need? The tangent inverse. But remember, there's an extra coefficient here, which should be 1 over a times tangent inverse of what? The rule says x over a. In this case, it's going to be x over 3 plus c. Any questions on that one? Because addition is commutative, this could appear like this, or don't be surprised if it appears like this, x squared plus 9. As long as you have the sum of two squares on the bottom, one has the variable, one has a constant, you can use tangent inverse function. But for the sine inverse, it has to be in that specific order because there's a minus in the middle, okay? Okay, let's take a look at the next one. Again, if you know your formulas, these are really easy. Okay, for this question, what will be our a? Good, it will be the square root of 7 because 7 represents a squared. So for this question, a is the square root of 7. So could somebody tell me the answer from the beginning to the end? Yes, Joey, 1 over root 7 times inverse tangent of exactly x over root 7. And by the way, some books, instead of tangent inverse, they use this notation, arctangent. It's the same thing. Tangent to the minus 1 or arctangent is the same thing. But this is what tangent inverse is not. Unfortunately, mathematicians chose a bad notation. When they chose tangent inverse of, let's say, 1, this does not mean 1 over the tangent of 1 or something like that, right? It just means the angle whose tangent is 1 is pi over 4, right? But it doesn't mean this. It's just they chose this bad notation. I don't know why they did that. Later on, to compensate for that, they said, oh, we don't like that notation because some people will think that's 1 over something from algebra. So they said, well, maybe we should use arctangent so to eliminate that confusion. But I think our book still uses, and many books still use this tangent to the minus 1 notation to represent tan inverse. Okay, this question here, could you use arctangent for it? No. What should we use for this one? U substitution. There's an x on the top, so let u be equal to x squared plus 7. Then du is 2x dx. So we come up here. What should I have for x dx? Right, from here you can see that x dx is the same as du over 2. And I put the du inside over 2 outside, divided by the bottom, x squared plus 7, which is now going to be called what? U. So we've seen this integral last time. This is natural log of u. In other words, natural log of x squared plus 7. Okay, I think I have like 1 or 2 examples left. I really want to give you like 15 minutes if I can for group activities today. So let's see if we can do the following 2 examples. Don't worry about the top one, please. I want you to worry about this one. This one is a little bit different than the other ones we've been doing. You know, there are 2 ways to do this question. One of them would be you need to put this in the same exact format as a good tangent inverse question. What is an extra factor here? That 2 doesn't make it look like a real, you know, arctangent problem. But you could try to factor out a 2 from both of them. You could say, I can write this as if I factor out a 2 from both of them, what will be the first one? 9 over 2, right? Because when you multiply, you want to get back to 9, right? What will be the second one? X squared, because when you multiply, you want to get back to 2x squared. So now it looks more like a standardized arctangent, except that that 1/2, I'm going to take it outside of everything. So now this looks more like a number squared plus x squared. Can I use arctangent right now? Or inverse tangent, same thing. But let me ask you guys, what is going to be my a here? Remember, this number represents a squared. It'll be 3 over the square root of 2. Would everyone agree with that? Take the square root of the top and the square root of the bottom. Okay, so the 1/2 came from that problem, so I'm keeping that. Who can tell me the rest? First thing you want is 1 over a, right, which is, right, basically turn upside down, root 2 over 3, right? That's 1 over a, correct? Okay, then I'm going to need tangent inverse of what? X over a, x over a, and that's like division by 3 over root 2, right? But there's another way to write that. How could you rewrite that? X root 2, or root 2x divided by 3, because you can just flip it and multiply with the top, of course. So I think that's the way you would normally see it in a book, so I'm going to rewrite it that way. This is the same as, combine all the numbers up front, root 2 over 6 times tan inverse of root 2x over 3 plus c. And the other way to do this involves u sub, but I think I'm just going to show you one way to do it for now. Later, maybe I'll introduce one more way. And the last example, before I go to it, any questions on this one we just did? Any questions? Yes. Right, the first step was to take out a 2 from the denominator, and then I also factored it outside of the integral sign. So now that is basically just sitting all the way outside of everything, the 1/2. And later, exactly, it was distributed with the remaining constants. Okay, the last question, of course, is probably the most challenging. You got something here that doesn't look like an inverse tangent. You got extra x term in there. X squared minus 6x plus 10 in the denominator. Okay, first of all, I'm going to forget about the limits. I'm going to factor out the 2. And for the bottom, I need to rewrite this. I'm going to leave some space. Some of you may see where I'm headed here. I left some space there. Guess what I'm going to be doing? Complete the square. Remember that from college algebra? Complete to a perfect square. You add and subtract something. What do you add and subtract? I'll give you the little rule there. It's like if you have a bx in the middle, so you basically take half of your middle term coefficient, you square it. You're going to add and subtract this number. What is half of negative 6? Negative 3. Square it. Square it. You get 9, right? So we're going to add and subtract a 9 then. Add a 9 and subtract a 9. If you do this, you are guaranteed to have a perfect square in the first 3 terms. These first 3 terms we're going to turn out to be automatically into a perfect square. And you can always achieve this by adding b over 2 squared, and b is your middle coefficient there. That is the perfect square of what, by the way? This is the perfect square of x minus 3. And what are we left with over here? Plus 1. Now does it look like arctangent? You don't have x squared, but you have x minus 3 squared. Close enough. You could do a u sub here, like let u be x minus 3, but you can skip that because du will be equal to dx. When that happens, you can skip the u sub and just go to the answer. The answer is, okay, what is my a here? X minus 3 is my variable. And what is my constant, the a? The square root of 1, which is 1. So what you want here is 1 over a, which is just 1. Tangent inverse of, instead of x, we have x minus 3 though, so x minus 3 over 1, or itself. In other words, just write it clean like this. Tangent inverse of x minus 3. And we had limits, right? 2 to 4, is that right? Okay, plug the upper limit in. Minus 4 minus 3 should be a 1. Minus, plug the lower limit in. And we've already done this one. What was tangent inverse of 1? At which angle sine and cosine are equal and the ratio is 1? Pi over 4. I told you guys this is going to come up a lot. It really will be coming up a lot. And then tangent inverse of negative 1? Negative pi over 4. So we get a plus in the middle, or 2 pi over 4, or pi over 2. So 2 times pi over 2. I think we're going to get pi. Did I do that correctly? Let me just double check. Pi over 4 plus pi over 4 is 2 pi over 4. And there was an extra 2 on the top. So we get 4 pi over 4, or just pi.